In the last video, we saw the symmetries of a regular n-gon, so a regular triangle, a regular square, a regular pentagon, are given by the dihedral groups, and that those consist of both reflections, flips, and rotations. Today, we're going to look at other shapes, or now we're going to look at other shapes. So we don't have to restrict ourselves to regular n-sided shapes. We can look at other shapes and ask what kind of symmetries do they have, remembering that a symmetry is an action that if I blink when the action happens, the shape is going to look the same afterwards. So let's look at these two logos. We have the Holiday Inn logo and the Pepsi logo. Ignore the coloring in both of these. There's not going to be any symmetry if we look at the coloring, and see if you can think about what kind of symmetries we have in each of these. So if we look at the Holiday Inn logo, we notice that we can rotate. So if I rotate it so that each of the like little blades of the shape fall on the next one, then this will work. I can't do any reflections here because there's no lines that if I reflect across the line, everything will fall in the same place, kind of because the fact that those little lines are skewed a little bit. So the only symmetries we have are rotations here. It looks like we have 7 different rotations, so I can rotate by that much, or I can rotate by this much, or by this much, and so forth and so on. So it looks like I have 7 different rotations. The amount that we're rotating by each time would be 360 divided by 7 degrees, which I don't think is a very nice answer. So we could describe those rotations as the do nothing. We don't rotate at all. We do a single rotation by 360 over 7 degrees. And then we do kind of rotate by twice this amount. We rotate by 3 times that amount, so forth and so on, up to 6. So we have 7 total rotations if you include the do nothing as a rotation. This is a group. We're just looking at rotations here with no reflections. We notice that if we do a rotation and we do another rotation, we get a rotation by one of these amounts. So this is closed. The identity, of course, is the do nothing. And then inverses, it's not too hard to show that, like, if I rotate by some amount, I can find another rotation that will get us back to the identity. This group we call C7. We'll talk a little bit more about that in a second. So this is not a dihedral group because it doesn't have any flips in it. If we look at the Pepsi logo, this again doesn't have any reflections because of the little like twist in the middle there. If I tried to reflect it at all, the twist would end up in the wrong spot. And the only rotation that I can do here is a rotation by 180 degrees. So if I rotate by 180, essentially the red and the blue switch spots. But since I don't care about color, then 180-degree rotation would work here. So if I do one rotation in this case, which is by 180 degrees, and I do the identity, the do nothing rotation, then this describes the symmetries of the Pepsi logo. This again is not a dihedral group because there's no flips here. And so this is going to be, we'll call this C2. We'll notice that the number here agrees with the number of elements in the group. We have this Ferris wheel at Hershey Park. So if we just kind of look at the main part of it and kind of ignore the blades coming out to the side, we notice that this one, again, no reflections are going to work here because of kind of the twirly shape of these. And we have, let's see how many rotations we could have. We can have 1, 2, 3, 4, 5, 6, 7, 8. It looks like there's 8 rotations, which should be the number of little blades here. So we're, in this case, rotating by 360 over 8 degrees each time. That's a single rotation. So the elements here would be do nothing, rotate by this amount once, rotate that by that amount twice, and up to rotating by that amount 7 times. We have 8 possible rotations here, no reflections, so not a dihedral group again. We're going to call this C8. Okay, these groups that I'm calling CN, these are called cyclic rotation groups. Cyclic might be coming from the fact that like things cycle, that we have rotations here. That word is going to be one that pops up again in our class. But a cyclic rotation group is the symmetry group for a figure that only has rotational symmetry, so no reflections. So remember with the dihedral group, we had reflections or flips as well as rotations. With a cyclic rotation group, we only have rotations. Okay, so we've talked about two different types of symmetry groups, and these are the only two that we're going to focus on. But we had our dihedral groups, which were Dn. These were the symmetries of an n-sided shape. These have n rotations and n reflections or flips. The number of elements is 2n. That's the order of the group. And this is a non-abelian group. The elements do not commute, or these are all non-abelian groups. Cn, this was our cyclic rotation groups. These described the symmetries of shapes that only had rotational symmetry. This contains only n rotations and no reflections. The order of this group is just n. There were exactly n rotations in here. And this group is abelian. Rotations commute with each other. Like if I rotate by 60 degrees and then rotate by 120, that's the same thing as rotating by 120 and then rotating by 60. Okay, so we have two different types of symmetry groups here. There's a lot of things in nature or like logos and things like that that pop up that have symmetry groups that are either a dihedral group or a cyclic group. So it's kind of fun to look at these. Once you start seeing some examples, then you'll see them all over the place, I promise. So look at these, and I'll actually have you do a project where you look for these in your real life. So this one's the Avery logo, Avery Paper Supplies. So think about what symmetries the shape has. Try and look at these shapes and see if you can think of what rotations they are, sorry, what symmetries they have before I talk through them. I'm going to notice that the Avery logo, it doesn't have any reflections. If I try and reflect because of this like crossover shape, it's not going to reflect to be the same thing. So it only has rotations, which means it's going to be a cyclic group. And it has three rotations. I can rotate here, here, or here. So this is going to be C3 will be the symmetry group of the shape. It just has three rotations in there by 120 degrees each. Let's see. Let's look at my hubcap. So ignore the little imperfection. So ignore the Ford logo in the middle and ignore the little like tire thing here. So if we kind of just look at this part in here, I notice that I can reflect if I reflect across that line or across this line or this line or this line, whoops, that line, then things work out. So I have, what was that? Three lines of reflection, or was that more? Oh, and I'm missing one here. So I have one, two, three, four, five reflection lines. And then rotationally, I can rotate by this amount, by this amount, by this amount, this amount, and one more. So I also have five rotations. So I have five reflections and five rotations. So this is going to be the group D5 would be the symmetry group for that one. Okay, we'll keep doing a few more examples here, but you hopefully can try these on your own. The Hong Kong flag, the flower, is not going to have any reflections because of, again, kind of that curly shape. It's not going to reflect perfectly, so it only has rotations. We've got 1, 2, 3, 4, 5, so we can rotate by 360 over 5 degrees each time would be our rotation. There's 5 rotations in here, so this is going to be the group C5. Okay. The Starbucks logo is kind of interesting. It can't be rotated at all so that it lands back on itself except for by 360 degrees. So definitely has the identity in here. But it has one reflection. We can reflect across that vertical line. Maybe I'll call that F for a flip. And so this is the whole group here. Because it has a flip in here, you would think it's a dihedral group, and it is. It has no rotations though. So we call this just the dihedral group D1. D1 turns out to be abelian because it only has 2 elements in it. So the dihedral groups are non-abelian as long as we have a 3-sided shape or bigger, but just kind of aside there. Okay, let's look at these. So the snowflake has both reflections and rotations. It looks to me like there's probably 6 lines of rotation or reflection. We've got 1, 2, 3, 4, 5, 6, and there will also be 6 rotations. So this is D6. Starfish again looks like I can reflect and rotate, so it's going to be a dihedral group. I've got, again, 5 reflections and 5 rotations. This is kind of essentially a pentagon. It's like a 5-sided shape, so it has the same um, symmetries as a pentagon, D5. BP logo, again, I can both rotate and reflect, so it's going to be a dihedral group. If you count the number of little petals here, this ends up being D18. I'll let you verify that. So we see there's a lot of logos that have symmetry in them because symmetry turns out to be pleasing to the eyes, both rotational, reflectional, and even translational symmetry, which we haven't talked about. So that's why we see a lot of symmetry in logos. I went to Spain last summer, summer of 2024, and you can find a lot of symmetry in tile work. So if we look at these, we're not going to describe the symmetry groups of these, but you could sit down and you could describe the symmetry groups of all of these. But if you just look at those, there's a lot of reflectional and rotational symmetry going on all of these. So these were just tiles on the walls or on the floors, decorations on doors and ceilings. So lots of fun things there. There's a lot of applications for symmetry groups. So in chemistry, these appear quite often. I have not done enough chemistry to be able to like fully understand these, but I guess chemists look at the point groups of certain molecules. And what they're doing there is looking at the symmetry groups of the molecules. And if they can understand the symmetry group of a molecule, then they can understand a lot of other things about these molecules. Yeah, including things that I don't really understand, but like molecular vibrations, chirality, which I have no idea what that is, polarity, light absorption. Maybe you guys understand those things better, but chemists use these symmetry groups. They're looking at 3-dimensional objects, so their symmetry groups are more complicated than what we're doing here in 2D. In biology, viruses are very symmetrical 3-dimensional objects as well. So scientists looked at the symmetry groups of viruses. You might have seen like a picture of the COVID-19 virus at some point in time, and you probably would have thought, hey, yeah, that looked pretty symmetric. The hope is that understanding the symmetry groups of viruses could potentially help find vaccines that work for different viruses. In physics, there's something called Noether's theorem, which gives a connection between symmetries and conserved quantities in physics, like angular momentum and energy. So kind of just interesting to point out that these things appear in other disciplines besides just math. Okay. For your asynchronous work this week, go ahead. This worksheet, I'll make sure it's posted here, but find the symmetry groups of each of the following, these 5 things here, and then also fill in that table from the first page, fill in the rest of the symmetries that we did not do in the previous video, which I erased before I recorded this one. So